Now let's look at how we can calculate the moment of inertia for composite area. In most cases, the cross section of element we want to calculate moment of inertia is made of familiar shapes. It most likely is going to be made of from some rectangle or any other familiar shapes. If there is a familiar shapes and we can split the original cross section to some familiar shapes, instead of doing the integration, we may able to calculate the moment of inertia for each of those parts separately. So let's look at a very quick example. For example, if I have an I shape beam like that, so and I want to calculate the moment of inertia for that. So one way is to go ahead like before and do the calculation. The other way is that I go ahead and break it into a couple of sections. So assume I want to calculate the moment of inertia for that about this x-axis. Assume this is what I want to calculate. So one way of doing that is to go ahead and to do the calculation. So assume this is the x-axis. One way of doing that is that I go ahead and split it into the known shape. So I can say that this one is made of 3 rectangles. So I'm gonna just break it to the some known shape, one from here and one from here. So I have top rectangle, the middle part rectangle, and the bottom rectangle. So in other words, for example, I have the top part, which is going to be this. So this is the rectangle I have it at the top, and then there's a rectangle that I have it at the middle, which is going to be this one, and then the rectangle I have it sitting at the bottom, and it's going to be, for example, this one. Another color. This one. Assume. So we have these 3 rectangles. So how we do that when we want to calculate the moment of inertia about that, for example, the x-axis, assumes the x-axis, we'll say that it is equal to moment of inertia for each of these 3 parts together, each of these 3 parts adding together. So the first one is going to be, so it's going to be the x-axis. So the first one would be this part, the very top part. So it's going to be this rectangle at the top. The second one is going to be the rectangle. This is the x. So it's going to be the middle part rectangle. So and we draw them exactly at their location wherever they are exactly are. And then we have the third one, which is gonna be this one down here. So the rectangle down here. Now if I have this one is Ix, and I would call this one the Ix1, so it's going to be equal to Ix1, so it's assume this is the area of 1, and then it's plus Ix2, so this is, assume this is the second cross section, and then cross the Ix3, 3 if this is the third cross section. So I need to calculate Ix for each of these three and just add them together to get this one. And here, if I look at that, for example, I do the calculation for this one. If I want to do the calculation for that one, I would say that I know its centroid is there, so it's going to be x prime. So its centroid is there, so I know that the ix1, for example, the ix1 is the ix one about its centroid. So its moment of inertia about its centroid plus its area times the dy1 squared, and the dy1 is the distance that we have between these two axes. So this is going to be d sub y1. So it's the distance between these two axes. The same for this one and the same for this one, and we calculate the using this equation, the parallel axis equation, and we calculate the ix1, ix2, ix3, and then we add them together. The only point is that, the only exception is that if there is a hole in this cross section, instead of adding its moment of inertia, we subtract it from the others. So if there is a hole, we do the same thing, but we subtract it from the rest of the inertia for our calculation. Now let's look at an example. Assume we want to find we want to calculate the moment of inertia for this cross section about the x-axis. So to do that, again, we look at that there's a hole in the middle of that, and when we look at that, we can write it as a known shape. So we will go ahead and say this one is equal to this shape, the full shape of that cross section, minus the moment of inertia of the hole. So minus the moment of inertia for the hole. And then the x is also here, so that's going to be the x axis, and the same for here. X is going to stay where it is, so x is always where it is, and want to do the calculation. So first we will do the calculation for this one, and for that one we know that the moment of inertia for its centroid, so if it's centroid, x prime. So now the moment of inertia for this one there, assume this is the 1 and this is the 2. So for the 1, the moment of inertia for the 1 is equal to moment of inertia about its centroid plus its area times the distance between the axes in the y direction square. So therefore the ix1 is going to be the moment of inertia about its centroid is 1/12 of b times h, and it's the b here is 15 and the h is 30. So it's going to be 1/12 of b, which is going to be 15 times 30 to the power of 3. So 1/12 of bh cubed plus the area, which is going to be 15 times 30, and then the distance between two axes, which is going to be this, is going to be the dy, the distance between the two axes. Let me put it here. say dy sub 1 so it's going to be uh, times, and the dy is 15 squared. So it's going to be and therefore the ix about the first axis, if we do the calculation, what becomes out at um, sorry, this is also 15, not 50. I made a mistake here. So it's 15 times 30. So if we do the calculation, then the result is 35, 0, 0, 0. So these are the moment of inertia for this one, and then it's going to be minus the moment of inertia for the ix2, and the moment of inertia for ix2, we know that is the moment of inertia about its centroid plus its area and dy, the distance between the axes, and therefore the moment of inertia for that one is going to be its centroid is the same as the previous one, so we've got both of them here, so it's the centroid, it's here. In this case they both have the same centroid, but if it was not this very similar calculation, so it's going to be 1/12 of bh squared, so the b here is 5 and the height of that is 10, so it's going to be 1/12 of b, which is going to be 5, times h, which is going to be 10 cube, and I write the rest here, plus the area, which the area is going to be 5 times 10, and the distance between the axes, which is dy2, and it's going to be the same as the previous one, in this case d sub y2, which is going to be the 15 squared, and therefore the ix2 would comes out at 11,666.66, and therefore so then the ix is ix for cross section 1 minus the ix for the whole, which would gives us 12, 33, 33.34 millimeter power of 4. So because we split it into the known shape, calculate the moment of inertia for each of the known shape, and then just add them if they are the solid and subtract them if there's a hole there. Now let's look at another example. Assume that's the cross section we have and want to find the moment of inertia about both x and y axis here. So it's the x axis and y axis here. So as you can look at that, we can split it into the three rectangle, the top rectangle, this middle part, and the bottom rectangle. So that's how I'm gonna first divide that into the three rectangle. So it's gonna be the x-axis for the first one. So we have the top part of that, and then we have the middle part of that, and the bottom part. Which is we sits down here. The bottom part of that section. And so to show how we split them, so we split them from here and another color, so we split it from here and here. So it's the top section, so that's going to be the top section, that's going to be the middle section, and then it's going to be the bottom section. So that's going to be part 1, section 2, and section 3. So it's going to be 1, 2, and 3. So we have these 3 cross sections. Now we can do the calculation. So one thing is that we go ahead and find the location of the centroid for each of them. So this is the location of the centroid, and if I draw the y-axis as well, so the y-axis here is going to be here for the top one, or draw it here. So that's the y-axis. For this one, the y-axis is going to be here, so that's the y. And for this one, the y-axis is going to be here. That's going to be the y-axis for each of them. So with each of these 3. And now if I find the distance to the centroid, so I know the distance for the centroid of this is, so this is going to be the centroid here for the very first one. So this is the x prime and y prime here, and therefore the dx and the dy for this one, this is going to be the distance between the, let me name this as well, so it's the x and x. So the distance between these 2 axes is also here, so it's going to be dy1, which is going to be from is a 60 and half of the width of that. So basically, let me show them on the, so for the top one, this is the centroid for the original one, this is centroid for this one, and this is centroid for this one. So if this is the C1, so it's the C1, that's the C2, and this is the centroid for the third one. So if this is the C1 here that we have, so that C1 is 60 plus half of that, which is 5, so it's going to be 60 plus 5. So it's distance to x-axis, and this distance here, and that we have it, is going to be the d sub x1, and it's from here to the y-axis, which is be half of this total distance, which is going to be 50 in there. For the second one, the centroid is going to be sitting here, so that's the centroid. So the dx is 0, the distance, the dy is 0, because also, so that's going to be the y prime, and this is going to be the x prime. So therefore the dy for the second one is 0, there's no distance between x prime and y prime, and this tiny distance here, just show it right here. So let me show it up there. This tiny distance here is going to be d sub x2, and it's going to be half of the width of this section, which is going to be 5. And for this one, for the last one, so the centroid is here, and this is the x prime, and this is the y prime. And again, the distance between the x-axis here, the dy sub 3. Let me write it off. So it's the dy sub 3, and it's the distance from here to the center of that, so it's a 60, and the half of the width of this rectangle down here, so the half of it is 5, and that's 60, so it's a 60 plus 5. And the distance here, which is going to be the d sub x 3, is going to be half of this width, which is going to be 40. So now that we split it into 3 shapes and we have the centroid of each of them, we can go ahead and start to calculate the magnitude. So for the first one, I would say that the I about x1 is the about its centroid, the moment of inertia about its centroid, plus the area, its area, and then the y1 squared. And we know that, okay, this one, the area about centroid is 1/12 of b, and the b is 100 here, so that the width of that section is 100 here, so it's going to be 100, and the height of that is 10. You can see the height of that is 10 times 10 to the cube, plus its area is 100 by 10, and then the dy here, dy1, is 65 squared. And if we do the calculations, comes out 42, 33, 33. Same for the I for the first section, so it's the moment of inertia about its centroid plus its area, and this time d sub x1 squared, so it's going to be 1/12, and this time the b and h replace its place, so it's going to be 10 times 100 cube, plus it's going to be 10 times 100 is going to be the area of that about the y-axis, and then the dx 1 squared, which is going to be the 50 squared, which is going to comes out 33 minutes. The same for the second one. If we want to write it for the second one, it's going to be I x2 is the moment of inertia for the second one about its x, about is plus its area and the distance between the axes to the power of 2. So it's going to be 1/12, and the b is here 10, and the height is 120. So the b is 10, the height is 120, so it's going to be times 10 times 120 cube, plus then 10 times 120, and the distance between its centroid and the x-axis is just 0. It's going to be 0. So what we will get is 144 0 0 0 0. And then the same for the y, for the second one is the moment of inertia about its centroid plus its area and the distance between axes to the power of 2. So it's going to be 112. This time we look at it from this way. So the base is 120 and the height is 10 plus, and again the area is 120 times 10, and the distance between the axis, the y prime and the y, is just 5 squared. So it's going to be and the same for the third one. So Ix for the third one is the I about its centroid plus its area and the distance between the axes to the power of 2. So it's going to be 112 and the base is here 80 and the height is 10, so it's going to be 80 times 10 cube plus the area, which is going to be 80 times 10, and the distance between x prime and x is 65. So it's gonna come out at 33, 80, 6666. And then the same for the third one about the y-axis. About the y-axis is moment of inertia about its y-axis plus its area times the distance between the axis cube. So this time again we look at it from the other way, so it's, the width is gonna here is gonna be 10 and the height is gonna be 80. So it's gonna be times 10 times 80 cube plus the area of that rectangle, which is gonna be 10 times 80, and then the distance between y prime and the y, which is gonna be 40 cube, and the result is going to be 176.666. So basically then the Ix is Ix1 plus Ix2 plus Ix3. This is going to comes out as 905.9999, and the Iy is gonna be I1 plus 2 plus the third one which would comes out at 507.9999 millimeter. So this is how we do the calculation. Just 2 points. Remember that here, for example, when we do the calculation about the y, instead of doing that, we could have directly calculated from the other equation, that from the base. We know that if it's from the base, we could have used the 1/3 of the bhq. So one more time, I just write the equation here in case that you want to remember them for the future. So if we have a cube like that, if we have a cube like that, it's going to be B and H, and we are having this x prime and y prime, or let's say it's the x and y, it's easier. It's the x and y, so x and y going through the centroid, therefore the ix is going to be 1/12 of bh cube, and iy is going to be 1/12 of hb cube. If we have the cross section, that is the same cross section, with the b and h, and this time the axis going at their base, so the ix here again is 1/3 of bh cube, and iy here is 1/3 of hb cube. And just to make sure we are not confusing them, let's put the prime here, and that's prime here, prime here. So these are the equation we have. So in case that we calculate the y2 from this equation, also we could have used this equation directly instead of using the parallel axis. We could have using, because all of them has the base on the y-axis. All of them has the base on the y, so also we could have used this equation as well.